service.
Talking about that.
Yeah. Okay, so we just had a power failure here, but we're back, and let me, I'm just going to very quickly go over what we've done so far, just so, to capture what we've done. So we went over the first problem for problem set 1, and what we found is that there was a little bit of information missing in that the hours per year were not given, but we went from 2,500 BTUs per hour, 1 million BTUs per decatherm, $5 per decatherm, popped that into Microsoft Excel, and decided that at that rate we would save 13 cents an hour. Then we just made a few estimates to say that if we run for 20% of the year with 8,760 hours per year, that would be $219 savings. If we ran for, let's just say, 50% of the year, obviously we would save more money. So that was problem 1. And then we went on to problem 3, which is here, the Tesla Roadster problem. And this is using box 8.2 from the textbook. So to get from 100 kilometers per hour, well, to get from 0 to 100 kilometers per hour looks like so. So here's just a little velocity as a function of time problem. In general, the velocity curve is going to look something more like this. It's going to be easier to accelerate earlier, and as you build up drag forces in the car, it's going to be harder and harder to accelerate. But anyway, we just assumed it was linear for the sake of simplicity. We used the energy equation. E kinetic is 1/2 mv squared. We know that we have to convert from kilometers per hour to meters per second to use consistent SI units. So we did that in Excel also. It's just a little bit bigger. So here's the mass of the vehicle. And what I'm showing you here are kind of, some best practices in Excel. So you've got the dimension of mass, basically, and you put the units in kilograms. You've got the dimension of velocity, if you will. We've got that in kilometers per hour. That's 100. And we know that there are 1,000 meters in a kilometer. When you write it out this way, it's easier to isolate your errors rather than bury that 1,000 somewhere. Just write it in a cell, because then you can come back and say, oh, I forgot there's actually 1,000 kilometers, in a meter. Maybe you typed 100 or something the first time you tried it. And so, Control-I. And we know that there are 3,600 seconds in an hour. So our first little conversion here was to take the 100 kilometers per hour. Yeah, there we go. 100 kilometers per hour. So now we can see the notes and the Excel at the same time. 100 kilometers per hour, 1,000 meters per second. Divide that by the 3,600 seconds per hour, and there you go. The car is traveling at approximately 30 meters per second, and we just kind of did a sanity check, and that means that it would take this car 3 seconds to cover a football field, which is quite fast, but not unreasonable. Okay, and then from there, we just found our energy. So we popped into our energy equation. E kinetic is 1/2 mv squared, and so this is going to be in joules, because a joule is a kilogram meters squared per second squared, as if you remember back from week 8, whatever it was. So there's that formula: mass times velocity divided by 2. So we're looking at about 500,000 joules. Yeah, so you could then say, oh, yeah, I think it would take me a half hour to get, if I were to just pull that car up to that speed, it would take me that much energy. Like if you're like winding a rubber band with a bicycle and you're going to slingshot this car, you'd have to pedal that rubber band for a half hour to produce enough energy to fire that car off, right? So then to find the power, remember power is just energy divided by time. So if you look at this figure up here, you could also, remembering the skills you've developed from problem set 3, we could sort of look at this. You could plot energy over here in joules. So at 3.7 seconds, you also have an energy value of about a half a million joules.
What were the calculations for the joules?
Yeah, so the joules, we used the formula that I wrote right off the top there. Energy kinetic is 1/2 mv squared.
Okay.
Yeah. Yeah. And then to get power, so obviously if this curve were steeper, so you can also kind of look at this curve as the car accumulating energy. So the bigger the triangle, the more energy the car has. And if it were going even faster, this line would be steeper. And so you think of that slope as the steeper it is, the more powerful the car is. It just accumulates more area under that curve more quickly. So to get power, again, all we're going to do is divide energy by time. We know that there are 746 watts in a horsepower. Memory serves me correctly.
I remember that number.
Okay.
That one sticks out for some reason.
Yeah, I don't know why, but there it is. And so then we just convert from watts to horsepower, and
Person power.
there you have it. Yeah. You can put it in people power too, right? So 168, which is, that's a lot of juice. It's not over the top. There's certainly more powerful cars out there, but keep in mind that this vehicle is relatively light, coming in at right about a ton. All right, so my computer is stable. I'm going to put this recording in the bank. I don't know if the first one made her in or not, but we did cover a couple good problems there. Yeah. All right. Yeah.